Welcome back to another 2011 FRC LabVIEW tutorial. We're going to be looking at the 2011 Vision Example program provided by FRC. This program takes an image and locates pixels in it that are within a color range that you specify. With these specific pixels, the program will attempt to locate up to 3 poles that will be on the FRC game field, and output the locations of these poles in an array. To simplify finding a color range that will detect the retroreflective tape that will be on these poles, we will be modifying the program slightly to give us the hue, saturation, and lumina values of any pixel in the image. After going through this program, the next step will be to implement it into an existing FRC robot project, and modify it to use the FRC camera to provide the images that the program will analyze. And this will be done in the next tutorial. To open up the program, click on Find FRC Examples, then go into the FRC Robotics folder, then to the Vision folder, and open the 2011 Vision Example LabVIEW project file. The main VI in this program is the 2011 Vision Example VI. The rest of the VIs are all used within this main VI. We'll begin by running the program to make it easier to understand what is happening. When the program is run, we need to select the directory in which the sample images can be found. So we'll go into the Images folder and click Current Folder to select it. We can select which image we want to use by clicking on any of the images in the list, and it will be updated in the image display labeled Original as soon as we select it. The next image display is labeled Threshold, and it displays a mask of the chosen image based on the color thresholds that are chosen. The 3 thresholds that can be changed are Hue, Saturation, and Lumina. Any pixel on the image that has HSL values within these thresholds will show up as a red pixel on the threshold image. Note that if the upper value of the hue range is less than the lower value, the threshold will wrap around and become all the values not in between these two numbers. To help us find ranges for these values, we can find the HSL value at any pixel in the image. To do this, we will begin by creating a property node for the original image display. Stop the program, right-click on the original image display on the block diagram, go into the Create tab, then go into the Property Node tab, and select ROI. ROI means Region of Interest, and we will use it to locate which pixel we want to know the HSL value for. We need to convert this ROI value to a point, and we'll do so by using a VI called IMAC Convert ROI to Point, which can be found by going into the Vision and Motion subpalette, then Vision Utilities, then Region of Interest, then Region of Interest Conversion. We will be using the X and Y coordinates at this point, so we'll have to create an unbundle by name function and wire the point output into it. Next, we'll need to get the HSL value of the pixel we have chosen, and to do this, we'll need 2 VIs, the IMAC Get Color Pixel Value VI, which can be found by going into the Vision and Motion subpalette, then Vision Utilities, and then Color Utilities, and the IMAC Integer to Color Value VI, which can be found in the same place. Now we need to convert the X and Y outputs of the point we will be using into the IMAC Get Color Pixel Value VI, so that it will find the color values at the location of the point. Next we need to wire the original image data into the image input of the IMAC Get Color Pixel Value VI, so that it will get the color values from the original image. Now wire the pixel value output of the IMAC Get Color Pixel Value VI into the U32 value input of the IMAC Integer to Color Value VI, so that the number is converted into a color value. Create a control for the color mode input of the IMAC Integer to Color Value VI, so that the color value can be changed from RGB to HSL, which is what we are looking for. Now create an indicator for the color value of the IMAC Integer to Color Value VI, so that the color value is displayed on the front panel. Now if we run the program again, click on the point tool in the original image display, and click on any point in the image. We will see that the values in the color value indicator change. If we select HSL in the color mode control, these values will give us an idea of what the HSL ranges will need to be in order to locate the target. To find a good range for the HSL values of the target you wish to track, you should find the HSL values of different pixels on the target. The more values you get, the better you can estimate what the HSL ranges should be. The HSL range you specify should include all of the values you have found in each category. You can also account for possible errors and missed pixels by increasing the upper values in each range, and decreasing the lower values in each range. Remember that these values depend on the environment that the images are taken in. So ideally you will want to go through these steps to calibrate these HSL ranges each time you use your robot in a new environment. A filter can be applied to the threshold image to remove some of the undesired pixels, which may not be what we are looking for. There are many filters to choose from, and you will need to experiment with different types of filters to see which one works best for removing unwanted pixels from your annotated image. By choosing the area parameter and turning on the filter, we can see that some of the smaller groups of pixels have disappeared. We can adjust the range values to determine which groups of pixels we want to remove from the annotated image. If the range button is enabled, the particles that are within the range of the upper and lower values will be filtered out. If the range button is not enabled, the particles that are within the range will be kept in the image, and the rest will be filtered out. If you need to apply multiple filters to the image to remove unwanted pixels, you can do so by increasing the row index by 1, and setting a new filter in this element of the array. Each filter that is created in this array will be applied to the image if the filter is enabled. The remaining components of the front panel are a histogram, the particle measurements array, and the columns array. These will be easier to understand once we have taken a look at the block diagram. These VIs are the dialog that asks the user for the location of the image folder at the start of the program. Each of these iMac Create VIs is an image, this one being the original image that is used, and these two each being one of the masks that are applied to the first image. The iMac Color Threshold VI is the first image mask. It applies the HSL thresholds to the image, and it produces the image display labeled Threshold. The iMac Particle Filter 3 VI is the second image mask. It filters the image according to what filter was chosen, and what the threshold values are for the selected filter. This VI only runs if the filter boolean is set to true. The iMac Particle Analysis VI will analyze each of the particles, and output the values that are specified in this array into the particle measurements array. Each value in this array corresponds to a column in the particle measurements array. Therefore, the first column in the particle measurements array is the x-coordinate of the center of the particle. The second column is the y-coordinate of the center, and the third column is the area of the particle, in pixels. More measurement parameters can be added to this array, and they will appear as a new column in the particle measurements array. The Find Poles VI takes these particle measurements and finds where the 3 poles are most likely located, by analyzing the particle sizes and locations in the image. This VI will output the columns array, which contains the middle x-coordinate of each pole, as well as the left and right side x value of each, measured in pixels. The VI also outputs a histogram, which graphs the number of particles in each group of pixels along the x-axis. The program determines where the poles are located by choosing the 3 groups of pixels with the most particles contained in them. Out of the 3 largest bars on the histogram, the left one is the pole that is to the left of the robot, the center bar is the center pole, and the right one is the one to the right of the robot. The final VI in this program is the Annotate Poles VI, and it draws a square around each of the 3 poles and produces the third image on the front panel. That covers the 2011 Vision Example VI. If you would like to know more about vision processing, check out the context help of the VIs discussed in this tutorial, as well as the other vision processing VIs. And also have a look at the National Instruments website to find more specific information about the topics discussed in this tutorial. Stay tuned for the next tutorial, in which we will discuss how to import the 2011 Vision Example program into your existing FRC robot project.